In this clip we will discuss the exploration of the limits of aircraft. During the Second World War, the technology of aviation developed very rapidly. New concepts were created like the jet engine, the radar, and a lot of other things. The jet engine was the beginning of the era of X-planes. In the abbreviation X-planes, the X stands for experimental. And the first X-plane was the Bell X-1. The Bell X-1 was the first aircraft which flew faster than the speed of sound. Up to that moment, the speed of sound, which is about 340 meters per second at sea level, was regarded as a barrier. Pilots who flew at speeds close to the speed of sound experienced intense vibrations and high drag forces. Just after the Second World War, the US was interested in analyzing this barrier and made this aircraft. On October the 14th, 1947, this aircraft flew faster than the speed of sound for the first time. This proved that the speed of sound was not a real barrier. In the slide you see that the speed of sound is also indicated with the Mach number. When this number is larger than 1, the airspeed is higher than the speed of sound. In the decades after the Second World War, many X-planes have been made. Most aircraft had a specific and dedicated purpose. Like the Bell X-1, some aircraft were made to explore super or even hypersonic flight. Other X-planes were designed for re-entry into the atmosphere, to have no vertical or horizontal tail surfaces, or to have thrust vectoring, etc. The latest X-plane is the X-57, which is an unmanned aerial vehicle to explore high altitude and long endurance flight. For an overview of all X-planes, I recommend you to look at the internet. Usually the number of aircraft built for X-planes is limited. Sometimes only one, sometimes a few. Also, the number of flights per aircraft was limited and often there were high risks involved, which meant that over the years a number of pilots have been killed during testing. I would like to introduce you to a few X-planes just to have a taste for you. This is the X-15. As you can see, this aircraft flew for the first time in 1959. Its main objectives were to fly at high altitudes at a very high speed. It is the fastest aircraft ever. It flew at a speed of more than 7,000 kilometers per hour, or at a Mach number higher than 6.5. This aircraft also had the altitude record for a long time, at an altitude of almost 108 kilometers. During the high speed, the aircraft was propelled by a rocket engine, and the skin temperature got very high, more than 650 degrees Celsius. Therefore, most of the aircraft was made of titanium and steel alloys. For cooling of the hottest sections of the skin, ablative materials were applied. Ablative materials mean evaporate and consume large quantities of energy. Another X-plane was the X-29. This aircraft had a forward swept wing. As you know, most airplanes have a rearward swept wing with a positive sweep angle. For metal alloys, this is the only option. Main reason is that for a metal wing, only a rearward swept wing results in a stable wing. A stable wing means that by increasing the angle of attack, the wing remains controllable. For composites, however, also a forward swept wing is possible. That's because composite properties can be tailored, which means the properties can be designed such that the stiffness and strength can be highly anisotropic. Let's return to the speed of sound. As mentioned before, we use the Mach number to indicate whether an aircraft flies slower or faster than the speed of sound. The Mach number is defined as the ratio of the airspeed v and the speed of sound a. Note that the speed of sound is not a constant, but depends on temperature. See the formula. When we look at airspeeds, we can define three flight regimes: subsonic, sonic, and supersonic. Subsonic indicates an airspeed below the speed of sound. Sonic speed equals to the speed of sound, and supersonic speeds are larger than the speed of sound. Another way to define flight regimes is on the right-hand side, when we name subsonic, transonic, supersonic, and hypersonic. If we look at the subsonic airspeed, we may discover the so-called Doppler effect. The aircraft flies from right to left and emits sound pulses and pressure waves. The sound pulse densify on the left hand of the sketch, and on the right side the distances between the pulses increase. When we stand on the left of the aircraft approaches with a high sound, dense sound pulses. Once it passed, the sound frequency drops. There are larger distances between the pulses. This high-low sound effect is caused by the Doppler effect. Note that the sound pulses do not come together in this picture. The coalescence of sound pulses and pressure waves happens at the speed of sound. Here the airspeed is equal to the speed of sound. This coalescence causes a pressure front or shock wave, which is a pressure step in the surrounding air. The pressure step also causes significant higher drag on the aircraft. When an aircraft flying at this speed passes us, we notice this pressure step in our ears. It is recorded as a loud bang. When we hear that, the aircraft is flying at the speed of sound or faster. In this sketch, you see an aircraft that flies supersonic, faster than the speed of sound. Again, a pressure step is generated and shock waves occur. But in this case, the shock waves have an angle with the speed of the aircraft. This is called the Mach angle, symbol mu. The sign of this angle is equal to the inverse of the Mach number. Sometimes that angle becomes visible, as in this picture. This fighter aircraft, an F-18 Hornet, is flying supersonic. Due to the pressure step, also other properties of the air, like the temperature, changes over the shock wave. This may cause condensation of the air, as can be seen in this picture. The angle of the condensation cones can be used to estimate the speed of this aircraft. This is a nice exercise for you to calculate the airspeed of this aircraft. Further, I tell you, this aircraft is flying at sea level. The shock waves have a negative impact on the flying conditions. The air resistance, the drag, will increase significantly. This can be seen in this graph. When a subsonic aircraft with straight wings tries to fly supersonic, its lift-drag ratio drops to very low values at the speed of sound. So what are possible solutions to fly supersonic? One of the applied options to overcome or reduce the effects of shock waves are the use of thin airfoils. Subsonic aircraft have thick airfoils with a round leading edge and a sharp trailing edge. The thickness of such airfoil is about 10 to 15% of the chord length. For supersonic flight, we use much smaller thicknesses, about 3 to 5% of the chord length. And both the leading edge and the trailing edge of the wing are sharp. This reduces the effect of shock waves and makes it possible to fly supersonic without too high drag forces. Another solution we can use is a sweep angle. If the wing is straight, or if it has a small sweep angle, the drag coefficient of the wing is high, at and beyond the sonic speed. Increasing the sweep angle reduces the drag coefficient, as can be seen in the plot. Therefore, all fighter aircraft and supersonic aircraft like the Concorde and this F-16 have high sweep angles and the leading edge, but a straight trailing edge. Such wings are derivatives of a delta wing concept. So improving the flight performance at supersonic speeds, we need to make thin airfoils and apply a high sweep angle at the leading edge. Sometimes the wings can be changed during flight, aircraft with so-called swept wings. Summarizing, since aircraft use jet engines, the airspeed has become very high. Most civil subsonic aircraft fly at speeds close to the speed of sound, with a Mach number of about 0.8. Military fighter aircraft fly at supersonic speeds, airspeeds well beyond the speed of sound, with a Mach number higher than 1. Flying at supersonic speeds induce high temperatures, requiring special materials. Supersonic flight also results in shock waves, which increase the drag forces. Therefore, we need to adapt the wing geometry. For supersonic flight, we use thin wings with sharp leading and trailing edges and a high sweep angle. In the next lecture, we will go one step further. We will go to hypersonic flight.